Hello, everyone. It's 1 p.m. Eastern, and that means it's time to begin our 84th CoCoRaHS Weather Talk webinar. A very warm welcome to all of you joining us today. I'm your host, meteorologist Henry Regis. Running the technical side of our program is our very own Noah Newman. We're coming to you live from the Colorado Climate Center here in Fort Collins, Colorado. All of our Weather Talk webinars are sponsored by the generous donations from listeners just like you. Well, today's webinar will look at flood warning systems, and that will be presented by Mark Moore, who currently serves on the National Hydrologic Warning Council Board of Directors as one of the directors at large and on the Alert Technical Working Group. Mark boasts 8 years in the flood warning industry as a hydrologic specialist. Though his skill with data remains uncompromised, Mark thrives most when he can help educate others about the priority of flood warning and safety. He often attends public outreach events and national flood warning conferences for the purpose of educating himself and others. Mark is originally from Pennsylvania. He moved to Texas in 2001 and graduated from the University of Texas with a degree in astronomy and environmental science. Well, let's give a big CoCoRaHS welcome to Mark Moore. Mark, it's great to have you with us today.
Thank you very much. Appreciate the introduction.
Well, as we start off our program, I ask this question to everyone out there, all of our guests, and that is, how did you become interested in weather and hydrology? Was there an event in your life, or what got you started?
Yeah, I think my interest in weather and hydrology, I kind of remember always watching the storms roll in, watching the, lightning strikes on the back porch. I moved to Texas just a few months before Tropical Storm Allison, which was a major flood event for the city of Houston. And then I just kind of kept the interest from there and couldn't really keep myself away from it when I continued on to college. So
that's neat. Everybody's got some kind of a story, and it's interesting. All of us in this field, how we got started, and it's usually some type of event. And Allison, in your case, well, I'm going to turn it over to you. You can show your screen, and we'll be back after your presentation with questions from our audience.
Great. All right, so we should have the presentation loaded. If not, just let me know. Otherwise, I'm going to go ahead and get started. So I'm going to talk about flood warning systems. I've been, as we just discussed, I've been kind of doing this work for about 8 years now. It's not a field of study that I thought I'd be in, getting a degree in astronomy and environmental science, but it's one that I've fallen in love with. And at this point, I can't see myself doing anything else. So, I really like talking about this, and I really appreciate the chance to share kind of some of the things I know and some of the experiences I've had. A quick agenda so that all of you listeners can know which parts you want to pay attention to and which parts you might want to ignore. So we're going to start off with, what is the NHWC? You've heard that acronym a few times now. I'm a director at large for the NHWC. So I'm going to spend a few minutes talking about what the NHWC actually is. Next, I'm going to talk about the warning process and flood warning systems in general. I'm briefly going to go over Alert 2 and how we send data. We're going to talk about measuring rainfall in real time. And last, we're going to talk about how CoCoRaHS helps to save the day. So what is the NHWC? Well, the NHWC is a nonprofit organization. It was founded in 1993 among an agreement between a couple of other organizations that were doing similar work. And our vision is to effectively use hydrologic information and warnings to protect lives, property, and the environment. And we achieve that vision through our mission statement, which is to provide education, training, and standards for the generation, delivery, and use of timely, reliable hydrologic information. It's a lot of words to basically say, we're monitoring rain, we're monitoring water levels, we're predicting flood levels. And our goal is to be a nonprofit that helps do that better, to help agencies, to help citizens, to help people who are out there in the field doing this type of work have a place where they can learn, where they can share their experiences, and where they can improve the type of work that they're doing. So the hydrologic warning is defined as the ability to warn of imminent danger to life, property, and the environment. So you might think of hydrologic warning as maybe a siren that goes off when floods are coming, or a gate that closes off a road. But it's more than that too. Hydrologic warning is turning on the news and watching the weatherman say, we've got storms coming, careful out there on the roads. It can be logging onto Twitter and seeing your emergency officials letting you know what's going on. Hydrologic warning is actually a pretty big umbrella term, but it covers a lot of what we do, and it covers a lot of what people deal with when they're going through weather events. So, when we're talking about the warning process for the NHWC, we like to compare it to a three-legged stool, because you need all three legs for the stool to work. So the first is to observe, monitor, detect, forecast, and generate the warning. A lot of people think that's it for flood warning, but that's really just one part of it. So observing and monitoring is what we're going to talk about a lot today. How do we get that data? How is it used? And how do we make sure it's accurate? But another part of that is that detection, that forecasting, and coming up with a sort of warning. Next, you have to disseminate that warning. You have to get that out there to the people, to the citizens, to the users of this information. And this can be one of the biggest challenges of flood warning systems. And then last is to respond appropriately. The warning process isn't complete if you don't do anything with the information that's been provided. And so at the end of the day, all three of these are very, very key aspects to hydrologic warning. Our nonprofit kind of covers a wide range of areas, including hydrology, data collection, modeling, standards and guidance, and public awareness. We put out a newsletter, and this newsletter can be found on our website. So anyone, even if you're not a member, has access to the latest version of the newsletter. It's put out once a quarter right now, and it's a great newsletter. It's got some really good articles, really good information. This is actually an article that I wrote for the newsletter back after Hurricane Harvey. We've got a board of directors, and our board is pretty much spread all throughout the country, and even a little bit international if you happen to catch that one right in the middle. Jimmy Stewart's in Queensland, Australia. But we've got people pretty much across the country, and we meet once a month as a board to discuss how we can do our job better. And then just to kind of wrap up that NHWC discussion, we put out a survey about 12 years ago asking our members, what do you want? What's valuable for you? And providing technical training through workshops was top of the list. Other things we saw was building a community, facilitating coordination at the federal, state, and local levels, providing public outreach, kind of like we're doing right now today, and being a national voice for local and regional hydrologic warning user groups. How do we do that training? Well, it's majority through local workshops. So we have workshops across the country. Just last month, we actually had one in Texas and one in Chattanooga. So we do these workshops to help train local agencies and local users on hydrologic warning. We also have an online webinar that's free to the public. That's usually about once a month. We do national conferences every other year. And then our website has a lot of resources for people to learn more. So, if you heard all that and you're interested in the NHWC, what can you do for the NHWC? We always encourage our members to serve on committees, whether it's a conference committee or a NHWC committee, things like data collection or training and professional development. One thing that is incredibly beneficial is writing an article for the newsletter. If you are out there and you're a CoCoRaHS observer and you have an interesting story to tell, we'd love to hear it. We are always looking for articles in our newsletter. And so my email address will be at the end of this presentation. If you have something you'd like to share, please feel free to reach out. These articles don't even have to be long. It could be a one-paragraph story with a cool picture of something you saw. So, if you're interested, let us know. And what does the NHWC do for our members? You kind of got the gist of it by now, but we are national representation. We do training and education, conferences, workshops, emails, newsletters. Basically, we're an educational agency. So that's kind of the pitch for NHWC. But what I want to spend a little bit more time talking about is flood warning systems. What are flood warning systems? How are they used? Why are they important? So if you Google flood warning systems, the first thing you're going to find is FEMA's CRS system. And I'm not going to sit here and read these 3 bullet points for you guys, but I want you to understand that, there are a lot of ways you can define a flood warning system. So, the first one that the CRS says, if you look at FEMA's, is a manual flood warning system. That's things like maybe physical gauges that you can see, or papers or tables, or, there's no technology really involved with a level 1 flood warning system. A level 2 might have some sensors. They might have some, phone calls, but they're not really in depth. A level 3 is really what we're going to talk about today. And those are automated flood warning systems. So these are things with a lot of sensors. They're measuring how high the water is and how much rain falls in real time. There might be forecasting involved. There might be responses, kind of that 3-tiered approach to flood warning we talked about earlier. So every flood warning system really should have a goal. And this is a goal that I stole from Harris County's flood warning system, because I actually used to work there for about 5 years. And I've always thought they had a very appropriate goal, which is to provide accurate and consistent rainfall stage and other data on a reliable real-time basis. That accurate and consistent rainfall stage and data line in there is really, really important. And that's why I was excited to be able to talk to you guys today, because we can only provide accurate and consistent rainfall data by making sure our information is right. And one of the tools we use to do that is CoCoRaHS observations. And so, you guys really do help us achieve our goals in flood warning systems. So when you're looking at a flood warning system, kind of the first thing you have to be aware of is, what are the flood hazards? Are you looking at local watershed flooding? That might be something, where it's creeks, maybe even rivers that start to flood out of banks. Maybe you have a dam upstream that could break or fail, or levees that could break, that you have sudden catastrophic changes. Maybe you have coastal flooding, tropical storms or hurricanes like we're seeing right now. Potentially flashy watersheds. I live in Central Texas, and that area is known as Flash Flood Alley because of the amount of rainfall we get and how fast that can cause our creeks to rise. This is a graphic that shows kind of what you might see in a flood warning system. And so at first, you're going to have these remote sensors. And these sensors are going to detect rises in water level. They're going to detect rainfall amounts. They might even have some weather sensors like wind, air temperature, and they're going to transmit it over the air to some sort of collection point. Traditionally, this has been done through terrestrial radio. So, protected frequencies that are only used for hydrologic warning. Now we're starting to see some cell-based and even some satellite-based ways to transmit that data. That data might have something local, like a siren or a flasher or a gate, but typically it goes to some sort of online server, where it's then distributed to a bunch of different places. For example, it might go directly to the flood warning system operators. We might also send it to emergency managers, to the media, or to the public at large. And at the end of the day, this is the goal, is to make sure that the data that we're monitoring out in the field makes it to the people who actually need to use it. So how do we monitor precipitation, right? Well, there's a few ways. Remote sensing it's kind of used all over the place, and that's using satellite or radar to measure rainfall. And then you can measure it at sites. So you can do automated gauges. We're going to talk about how we measure rainfall through automatic gauges coming up soon. But field observations is also used. And this data can be ingested into flood warning systems or to flood warning models. And that's done all over the country. We also will measure the stream. Rain is only part of the story when we're talking about flood warning systems. The other part is what actually happens to that water once it's hit the ground. And so we can do that through automated gauges or through field observers. You might have a staff gauge out there, kind of like you see right here, where it can tell you how deep the water is. In this case, maybe 1.4 feet. Or you might have a wire weight on the side of a bridge. And this is a device that just has a manual readout of how high the water is. And then last, you might actually just have an automated gauge that's providing that information in real time. There are a couple different ways that we monitor water levels in real time. One of the most traditional ones has been a pressure transducer. And what a pressure transducer does is it's actually got basically a pressure sensor on it. And as the water level goes up, it pushes and pushes and pushes against that sensor, causes the pressure to rise. That pressure rise can be translated to how much water there is. And that information can be sent almost instantaneously. So pressure transducers, there's probably thousands of these out there monitoring streams and creeks and rivers all across the country. Bubblers are a little bit of a newer technology, but they're not that different. This is an example of a bubbler right here. Bubbler, what it will do is it'll actually push air through a tube into the water. And when that water resists that air movement, it builds up a pressure back through the tube. That pressure is read by the bubbler, and it knows how high the water is. In a way, a bubbler is just a fancy pressure transducer. Stilling wells have been used for a long time. What they do is they have a float on one end and a weight on the other. As the water rises up, it causes the float to go up, and we can actually monitor that position of the float and know how high the water is. Radars are one of the newest sensors on the market, and when I say newest, I'm still talking about a decade or two old. Radars use electromagnetic pulses and measure the response time to see how far away the water is. Kind of like a radar gun you'd see if you're getting caught by a police officer, but rather than speed, we're only measuring distance. When we put these sensors out there, we have to consider a lot of things like, do we put them on the upstream or the downstream side of a bridge? Because it turns out bridges are great for us. If we want to know how high the water is, having a bridge across a creek provides a lot of places for us to mount our equipment. But do we put it on the upstream or the downstream side? And that's a question that ends up being system specific, depending on if you're worried about maybe things blocking at the bridge and causing some upstream flooding, or do you want that protection you might get on the downstream side? That all starts to come down to your system goals and what you're trying to monitor. You also have to consider, what does your site look like? If you have it on the side of a bridge, kind of like this picture here, how easy is it to access? Is there a safe place to park if you're doing maintenance on the gauge? Is there anything that's going to get in the way of your water sensor? The previous slide, we're talking about these radars, which are great devices because they're up out of the water, they're maintenance free, and they're very, very accurate. But what happens if you have boats or kayakers that go under your bridge? Not a good place for a radar. So that's something you also have to think about when you're talking about your site considerations. Is there known vandalism? Are there a lot of trees nearby that are going to impact your rainfall collection? This is an instance where we actually co-located with a USGS gauge. The USGS is the United States Geological Survey. They've got gauges all across the country, and they provide very accurate rain and stage information. One of the limitations of their technology, though, is that it can only transmit data once an hour, at most maybe once every 15 minutes if there's a major flood event going on. Even 15 minutes can be too far delayed for effective flood warning. And so what we'll often do for flood warning systems is we'll incorporate our equipment in their enclosure so that we can get all that information in real time without impacting their ability to take those measurements. And so these are all things we think about when we're talking about site considerations for installations. So I mentioned a few times now that we transmit in real time. We're getting this data instantaneously. What I'm talking about typically is alert or alert 2. So alert is actually an acronym in the flood warning community, and it stands for Automated Local Evaluation in Real Time. Exciting. Well, what it was is that, especially in the 60s and 70s, people started to look at the technology we had available and the issues that we had at hand and kind of came up with a way to solve some problems. Places like California and Colorado specifically, we'd see these rain events that would happen up in the mountains where there weren't people, there weren't telephone lines, there weren't ways to get communication out of those mountains, but they'd flood the valleys and they'd flood the downstream communities. And you'd get flood waves with absolutely no warning coming. And so they developed this technology of, all right, what's a way we can monitor that rainfall in real time? And so it's developed in the 1970s, and it's an incredibly efficient way of sending data. You can barely tell on this picture, but there's actually a solar panel on here. That is a 2.5 watt solar panel. And that little tiny 2.5 watt solar panel is plenty of power to run this gauge indefinitely. So these are gauges that are put out there. They can be up on mountaintops. They can be, way off the beaten path. They can be completely remote, completely independent stations running on just solar power. And just a tiny little 2.5 watt panel, and that will keep the gauge running for as long as the equipment keeps working. And so this technology, we look at it nowadays, it seems outdated, or it might seem old or inefficient. But at the time, first off, it was, the latest and greatest new technology. But even today, the fact that you have something out there that requires so little battery power and can work so reliably is amazing. And so alert stations took off across the country. And by the 1980s and 1990s, there were thousands of these alert stations out there. They work on a one-way basis. So when it detects rainfall, it's going to send a radio message, and it sends us data as a radio chirp on a frequency that can only be used for hydrologic warning. And so the other advantage we have with these systems is that we don't have to worry about someone else coming and, trying to sell off that frequency, because it is protected for hydrologic warning. Now, one thing that will happen is that, the government will sell off chunks of those frequencies. So we often do have to defend ourselves. And that's something the NHWC does, is try to protect those hydrologic frequencies. There are some issues with alert, though. I mentioned that it sends data whenever it rains. It sends off this chirp. Well, what will happen is that if one gauge sends off a chirp, at the same time another gauge sends off a chirp, that data will actually get corrupted. If you've got 20 gauges, the likelihood of 2 of them going off at the same time is pretty low. If you've got 300 gauges, the likelihood is pretty high. So this is an analysis that was done of a system on that alert protocol, where they're looking at the hourly number of messages, that's on this right axis right here, and they compared it to the percent of data that was lost. That's this axis right here. So once you started to reach 6,000 to 7,000 messages an hour, that system started losing 35 to 45% of the data. And if you think about that for a moment, not only are we losing 45% of the data, we're losing that when it's raining the hardest. And so I've talked about the fact that we need reliable, accurate, and real-time data. Well, we're losing that reliability when the system has too many gauges transmitting at once. And this ended up being a problem that would severely impact large systems across the country, because as they developed, they kind of developed at their own scale and at their own pace without considering how much those gauges might impact when you have 200 or 300 gauges sending 7,000 messages an hour, losing 45% of your data. So obviously this wasn't acceptable. And about 10, 15 years ago, the NHWC kind of pulled some experts together and said, how can we fix this? And what came out of that was the Alert 2 Technical Working Group, which developed the Alert 2 protocol. One of the biggest changes for Alert 2 is that each gauge is actually assigned a time when it's allowed to talk. So it can't transmit randomly, it has to transmit during its assigned position. Everyone basically has to wait in line, and your spot in line is assigned. Another advantage is that data is sent in engineering units. So we're sending things with actual decimal points, which requires no rounding and it requires no weird conversions. And the biggest advantage is that you don't lose data during weather events, because again, every single gauge has to transmit in its assigned slot. Each gauge gets about half a second to transmit. And so, you might be able to get all your gauges within a minute or two. Is it still, local evaluation in real time? Yes, but we are starting to see, more like a minute behind or maybe 2 minutes behind. But that comes with the reward of receiving 100% of your data. So this is a system that was alert based in 2012, 2013, and 2014. And if you look at the percent of data that was received, these blue bars represent the percent of data that came in during a weather event. And it got maybe 50% of the data during a weather event in 2012, a little bit better because some improvements happened, but you're still only getting about 60 to 70% of your data. The conversion from alert to alert 2 happened in 2015. And then in 2016, they're getting pretty much 100% of their data. I mean, we're talking about 99.8, 99.9% of data. So alert 2 has been proven to be a very successful way of monitoring flood warning systems. Now, it's not the only technology out there. As I mentioned, over the past 5 to 10 years, we've been seeing more and more cell or more and more satellite-based systems out there. And what it comes down to is everything's a bit of a compromise, because you might have a cell-based system where a hurricane hits and the cell towers go out and your gauges don't work. Or you can have a satellite-based system and that satellite provider has an outage Alert and Alert 2 have their limitations where it's kind of complex to set up, or you still have radio towers. So how you send your data, there's a couple different options and a couple different ways to do that. And it comes down to the goals of your flood warning system. What are you trying to do? What is the purpose of your organization? And what are you trying to provide to your public? So let's kind of dig into the meat and potatoes of flood warning systems. Now we know how they send data. Now we know kind of how they work. I like to call this talk the good, the bad, and the ugly. I'm going to kind of pick on Harris County for a little bit because one, they've got one of the best flood warning systems in the country. And I don't say that just because I used to work there, but I also worked there for about 5 years. So I know their system pretty well. So let's talk about the good, the bad, and the ugly. All right, the good. When a system's well maintained and it's improved, people take notice. So this is a screenshot from Harris County's flood warning system. And they have a publicly accessible website. You could go on there right now and you could see this data. During Hurricane Harvey, they received over 7 million website visits to this public website. Now I can tell you right now that that website crashed because it was not designed to handle millions of people a day looking at it. So that 7 million page views is the people that managed to get there. There were even more attempts to actually look at this data. So in a way, that's good. The public knows about this. They're looking at it. They're reading the graphs. They're looking at rainfall totals. That's what we want to see. The bad. When a single gauge goes out, everyone notices. So this is a just kind of zoomed in shot of that flood warning system. These are rainfall totals in inches. So 1.3, 1.5 inches, 1.4 inches, 1.2 inches, 0 inches. These gauges are maybe a half mile apart, if that. Clearly something wrong happened at this gauge. 0 inches of rain. You might see something similar on your CoCoRaHS reports. If you have two observers that have something very different, that raises some red flags of maybe something's wrong. And when you get issues like this, that can reduce the trust in the system. The ugly. When people trust your data, they treat it as absolute truth, even when it isn't. So this is a tweet put out by the National Weather Service during Hurricane Harvey, saying that the continental US rainfall record was broken at this gauge. It says Cedar Bayou at FM 1942 received 51.88 inches of rain during Hurricane Harvey. They did say this is a preliminary report, but 51.88 inches of rain. If you Google Hurricane Harvey rainfall, 51.88 inches, you get 37,000 Google results. This is a known number for Hurricane Harvey. This was on Wikipedia for Hurricane Harvey for a while. This is what the gauge looked like. So this is the inside of the gauge that was completely water damaged. This is the water level sensor. It's one of those radars we mentioned that got snapped by debris coming down the creek. And this is how high the water got into the box. The battery's at the bottom of this box. The water was above it. So what happens when these gauges flood? Well, let's take a kind of close inspection of the rainfall for a moment. The first day of Hurricane Harvey, we were at 40 inches of rain for the year. In Texas, our water year starts January 1st. So January 1st to August 25th, we had received 40 inches of rain cumulative at this site already. It starts raining, and we have a reasonable rise of rainfall, couple breaks, rain. August 26th, we see some pretty significant rises of rain, about 5 inches of rain, get a little bit of a break. August 27th is when the rain really starts to fall in Harris County. So we go from about 45 inches of rain to 60 to 70 to 80. And, depending on how well you can see the screen, it gets really linear at the end. Well, let's take a closer look, because rain is not linear. In fact, it gets to a perfect line. This is when the gauge flooded. When the gauge started to go underwater, every minute when the radio would power on, it was actually sending a tip of rainfall. And so this was bad data. This is not accurate. This last push of rainfall was wrong. And that's the ugly, is that when people really start to trust your data, they might treat it as absolute truth, even when that's not the case. So how do we measure rainfall in real time? I've shown you how we display it, and I've talked about how we transmit it. How do we actually measure rainfall? For Harris County, they use something called a tipping bucket. And it's a really simple way. It's been used for decades to monitor rainfall, and it's an accurate way to do so. So what happens is that you've got a funnel above this where the rain comes into the secondary funnel, and it's going to fill up this bucket right here. When that bucket fills with water, it will tip. When it tips, this little magnet arm is going to go past a reed switch, and the data logger can actually monitor each time it tips. So all we're doing is we've got a seesaw, and as that seesaw goes back and forth, we count how many times it goes back and forth. And for that Harris County system that I was just showing you, each tip is about 0.04 inches of rain, 4/100ths of an inch of rain. So, 40 inches of rain is a lot of tips. Tipping buckets have advantages and disadvantages. The good is that they are cheap. They're reliable. They've been used for decades, as I said. You can make sure they're accurate. You can calibrate them. They've got very simple wiring, and they're compatible with pretty much all the equipment out there on the market. The bad is that they're maintenance heavy, that these funnels can clog. The tipping bucket mechanism can get stuck. I've seen ones that fail where they get stuck halfway in between. They require regular calibration. They're less accurate with heavy rainfall, and you have a leftover rain issue where maybe there's enough rain that it almost causes it to tip, but it doesn't. What do I mean with that rainfall rate? Well, if we look at this tipping bucket, when rain is falling into this funnel, it'll actually start to make that seesaw move when it tips. While the bucket is tipping, it's not collecting rain. And so when it's raining heavier, more rain is lost because that bucket is tipping back and forth, but it loses the collection during that tip process. It might not sound like that much, but when you start to hit rainfall rates of 2 inches an hour, you'll start to notice it. 4 inches an hour, it's maybe 5% error. 6, 8, 10, 12 inches an hour, you start to hit that 10 to 20% error with a tipping bucket. That's not very typical. Usually you don't see rainfall rates that long, but they do happen, especially in tropical locations, and tipping buckets can start to fall behind. Weighing buckets are kind of a way around that. The National Weather Service defines weighing buckets as optimal for use. What they do is they actually measure the mass of the rain through a scale. And so anything that falls into this bucket gets weighed by a very accurate scale. They are great devices. They are often used at airports. They're often used at official weather stations. They are very precise. So the good is that they're accurate, reliable. You can calibrate them. The other thing is that they can measure snow and hail. So that's great. And they're not dependent on rainfall rates, kind of like tipping buckets are. There's still some bad. One is that funnels can still clog. Two is that they have to be emptied after a certain amount of rainfall. I believe most of them are about the 10 to 20 inches of rain. Hurricane Harvey in Houston wasn't 52 inches of rain, but it was close to 45 inches of rain. And there's 300 stations. And so it'd be going to 300 stations and emptying them once a day during Hurricane Harvey. Not at all practical. So it doesn't work for a large system. They're also expensive. We're talking about 5 to 10 times the cost of a tipping bucket. And they might require some more sophisticated equipment to monitor them. Distrometers are kind of a new, easily accessible way to measure rainfall on the market. So a distrometer is just a drop counter. And in this case, this distrometer actually measures the drop size through a little sensor. It's like a drum on top of it. And when rain falls on this sensor, it's like the beating of a drum. And it can calculate how big the rainfall drops are. It can calculate how many times that happens. And you can get rainfall rates and rainfall amounts through that. So the good things about these is that they're very easy to install and very easy to maintain. There's no funnels that get clogged. There's no leaf debris. There's none of these rainfall rate issues. You don't have to go and empty them. Those metal drums that get hit, they can actually detect hail and report it separately from rain. And they're very simple to include in a system. The bad, you can't calibrate it. You're kind of hoping that whoever programmed it right, because you're not going to be able to test that it's reporting accurate rainfall. We've done some testing and we found them to be not very accurate. We see error rates of about 5 to 10% off from true rainfall rates. It's not the worst error in the world, but we strive for the best accuracy we can. We've also seen some false positives from wind or even nearby train tracks. And so that's a concern. And then the last is that those sensors, they might get covered by like bird droppings or spider webs, other things that can impact the sensor. Drop counters are also often used for measuring rainfall. They're kind of like tipping buckets, but rather than have a mechanical tip that goes back and forth, you've got a little diode or electrode right here. And when an amount of water flows through that, it's going to short circuit it. And all you have to do is set up your data monitoring device to look for that short circuit and count each one of those as a drop of rainfall. Then you just correlate drops of rainfall to rainfall amount, and you know how much rain's fallen. The good, they're very cheap. This is probably one of, if not the cheapest way to measure rainfall automatically. They're also reliable. You can calibrate them, and they work okay with high rainfall rates. The issues is that, well, you still have a funnel that can clog. They still require some regular calibration. They're not as accurate when it comes to rainfall intensity because it has to go through the drip counter. And generally speaking, they're less accurate than a tipping bucket. Last I'm going to talk about is radar Dopplers. These are another one that you'll often see at maybe your DOT, Department of Transportation weather stations, or airports. They work by also measuring drop speed, correlating that drop speed to drop size, and then you can use calculations to get to the total amount of rainfall. So the good and the bad here, they're very low maintenance, they're very easy to install, and they provide more information than just rainfall. The bad is that they're very expensive. They have very high power consumption. You could not run one of these on those tiny 2.5 watt panels that we were showing earlier. The accuracy, it's kind of up in the air. If you look at the specifications, they don't really say how accurate they are. You can't calibrate it. And they're not as tested when it comes to something like a tipping bucket, which has been used for decades. So that's kind of a short sampling of the ways we monitor rainfall. There are other technologies out there, and there's things that we're testing pretty much every year, trying to find that sweet spot of affordable, accurate, and easy to maintain. And none of these sensors really fall into that. The closest one today is still the tipping bucket. Doesn't matter what sensor you have, you've still got to put it in the correct place. So if you ask me where I'd rather spend a weekend, it's going to be this picture on the left, in the forest, surrounded by trees, in with nature. But if you ask me where I'd rather install a rain sensor, it's going to be this picture on the right, because these trees are going to impact rain collection. You're going to have, we aim for what we call a 45-degree cone of free and clear above the rain gauge. And these trees would clearly get in the way. Whereas something like this is nice and open and wouldn't have the impacts from the trees. So again, site parameters can have a bigger impact, much more than what sensor you have out there. It doesn't matter if you've got a drop counter or a tipping bucket or a distrometer. If you've got a tree right above you, you're still going to have issues getting accurate rainfall data. So things to consider: trees, buildings, traffic, right? Are you going to have trucks on a big bridge moving past? Because we've seen this where trucks will actually cause a bridge to bounce, which can cause a tipping bucket to tip. How well can you maintain it? How high is it above the ground? Vandalism, wildlife. How valuable is this location? My company's motto is no data is better than bad data. And that comes from the fact that we won't put equipment out there if it's not going to measure accurately, because we need the public users of these systems to trust the information that's provided. And if we put a system out there and we put rain gauges under trees, they're not going to trust it. We're going to be providing bad data. And at that point, we're not providing the service we need to be providing. So I'd say, when we're talking about these automated flood warning systems, site evaluation ends up being way more important than what type of sensor you have out there. That's not to say we're still not interested in what sensors are out there. This is the one equation I'm going to show you guys, and I promise we're not even going to go through the math. I just wanted to show this because this was an interesting study showing what happens to rainfall accuracy depending on certain factors. Some of these might apply to even your CoCoRaHS gauges. Some of them are kind of specific to automatic gauges. One is the loss of rain collection due to wind. So what you'll have out there is you'll have these tipping buckets or any sensor that's usually a cylinder. And when the wind comes, it's going to hit that cylinder and it's going to blow up. That has the potential to deflect wind out of the collection gauge. And it's based off of wind speed, which is often based off how high your gauge is. So generally speaking, we like to keep our gauges lower to the ground to get less impact from wind. For automated flood warning systems, when we're talking about a system of 300 gauges, it's tough to get it close to the ground. And that's because if someone sees a gauge close to the ground, they're probably going to mess with it. And so it's always a balance of keeping it away from vandalism, but also not putting it 50 feet in the air where it's going to have some wild data due to wind. One thing that's not always considered with these automatic gauges is losses from wetting on the walls of the collector. Those first couple drops, that trace that you might see isn't going to be reported by these automated flood warning gauges because that's just going to stick to the walls of the sensors and eventually evaporate. Then there's also that loss of evaporation itself. As I mentioned, if there's any leftover rain that doesn't cause a tip, you can see some error because of that. Splash in and splash out isn't too specific, but what you'll have happen is, you might have this funnel that's collecting rain. And as the rain falls into the funnel, some of those drops might get pushed back out because we put screens to keep leaves and debris from getting in. And then, blowing and drifting snow. I live in Texas. I don't think about snow too much, but that's something that can also impact, if it's blowing very heavily and you have snow being pushed into your collection device, that's not actual snow amounts, but that's something that might get recorded accidentally. As I mentioned, I'm still interested in what sensors are out there and how they work. So this was a temporary setup by our company where we wanted to test this. We wanted to know which rain gauge is the most accurate. And so in this picture, you will see 6 different rain gauges that we talked about. We've got 2 different distrometers. We've got the radar here. We've got a tipping bucket here, a bigger tipping bucket in the background, and then a drop counter here. 6 different ones. And these gauges were put out there for about 3 months. And if you look across the entire range, we saw anywhere from 9 to 14 inches of rainfall, depending on which one was used. And I'm not going to go into the details of which one was better or which one was worse, because if you really start to dig into those details, it was kind of storm dependent and rainfall intensity dependent. Just know that of all those sensors we were talking about, we might be talking about 30% deviation from what's true. And how do we know what was true when we were doing this study? There was also an unpictured CoCoRaHS gauge at this location that was monitoring that rainfall as well. And so, we talk about all these ways to automatically monitor rainfall and automatically keep track of that. But honestly, if you ask me, one of the most accurate ways to measure rainfall is through a CoCoRaHS gauge. It's through having a known set standard that's monitored regularly, where you don't have to worry about these tips or technology or things that might cause failures. We use CoCoRaHS gauges as our gold standard for comparison. When I was at Harris County Flood Control District, we had a CoCoRaHS gauge in our parking lot next to our weather station, so we could always compare the two. And we always trusted the CoCoRaHS gauge as the more accurate. The issue is that we don't have 300 people in someplace like Harris County out there checking the CoCoRaHS gauges once every 2 minutes and giving us a phone call. So it's not the be-all end-all solution in terms of flood warning, but it is certainly the gold standard of making sure that our flood warning equipment is working the way it should. So just a few conclusions about how we monitor the rainfall before I talk a little bit more about CoCoRaHS and how we use CoCoRaHS data. Site selection and proper maintenance, way more important than what type of sensor you have out there. You still need to know what's good and what's bad about different sensors, and you really should calibrate your sensors. After Hurricane Harvey, one of my jobs was to go out and check different rain gauges that had reported, the most rain ever in Texas. A lot of these gauges were things like backyard weather stations that might have a tipping bucket inside them. And what I found when I was doing calibrations on those is that those tipping buckets sometimes, of the backyard weather station variety might be 20, 30% off. For something that is monitoring rainfall in your yard, you might want to know about irrigation. That's fine. But for running a flood warning system, they just weren't meeting the specifications. And, we couldn't trust those as being the maximum rainfall either. This picture actually shows one of the rain gauges during Hurricane Harvey or after Hurricane Harvey. That is mud and silt and sedimentation from the river. That's about 15 feet off the ground and was about 20 to 30 feet above the river at the time. Rain gauges don't work that way. That is a tipping bucket that got so underwater during the flood event that the tipping bucket itself was submersed. Just an interesting photo there. I'm going to wrap up my presentation just talking about, your measurements, you CoCoRaHS members, and why those measurements matter. And so, this is a quick quote from Jeff Lindner, who runs the system down in Harris County and was the CoCoRaHS coordinator until it was passed on to someone else. That said, grassroots rainfall reports determine what's actually happening. The more volunteers and rainfall data we have before, during, and after events, the better we can define how much has rained and what those impacts are. This is a system that's up outside of Denver. This is the Mile High Flood District, recently renamed, so kind of catch myself there. Their website actually shows both CoCoRaHS and alert or alert 2 gauges. If you look at historical information, they ingest CoCoRaHS data and they put it on their website, just like their automated data. All of their post-event reports use CoCoRaHS data, just like their automated data. So this is an example of an integration of flood warning and CoCoRaHS on one website. Another one, if you have some time, this is a very easy to read article in the Texas Water Journal, which is talking about the integration of the CoCoRaHS observations into the West Gulf River Forecast Center's operations. I'm going to pull a few slides from that. So CoCoRaHS data in use. What happened is they were getting rainfall estimates from their radar. This is places where there weren't automated rain gauges. There weren't, airport weather stations. The only information for this data was CoCoRaHS observations. Because if you actually look at where Hurricane Harvey made landfall, usually it's Houston and Beaumont that are talked about. But it's actually further south along the coast in some counties that just aren't very populated and don't have automated flood warning systems. And so the West Gulf River Forecast Center was actually looking at CoCoRaHS data and using that in their models more than their own radar data. This shows day 1 of Harvey. And on the left side, you can see the CoCoRaHS observations. And on the right side, you're going to see what they had actually used in their radar. And so some of these are pretty close, 9.6 to 8.6. Okay, the CoCoRaHS gauge was within about an inch of their radar estimate. Some of them, we're looking at almost 9 inches of rain to about 5 inches of rain. Their radar estimate was 4 inches low. Again, CoCoRaHS here is being used as the gold standard, and it's being used to adjust their radar for all of their forecasts, for their information, for the data that goes out to the public. They're monitoring what the creek levels are. They're predicting what the rivers are going to rise to. They're making evacuation decisions based off of this. And this could only be accurate because of the CoCoRaHS data that was collected. Here's another one showing the 10 highest CoCoRaHS gauges on August 27th. A lot of rainfall at those CoCoRaHS gauges, right? We're looking at 21.6 inches of rain collected at this observation station for CoCoRaHS. And the radar estimate is only 12.9. You'll notice that these are all 12.9. That's because the radar estimates are based off of block grids, and all of these readings were in the same block grid. And these CoCoRaHS readings, they're reasonably close together. I mean, this isn't an observer making a mistake. These are significant observations that are providing true information way higher than what the radar was putting out. And this is what was used to calibrate the models, these CoCoRaHS observations. So this picture on the left shows Hurricane Harvey and its rainfall estimates on day 2 of Hurricane Harvey. And it's kind of hard to see the colors, I know, especially through a presentation, but this is before the CoCoRaHS data was ingested. And you can see that like the highest rainfall is kind of got a small dot here and a reasonable sized patch here. And then after the CoCoRaHS observations, these patches got a lot bigger because they had a much better understanding of where the rain fell and how much had actually fallen. The article concludes that the CoCoRaHS observations helped improve the lead time on the magnitude of flooding. The initial estimates were low, adjustments were made in real time, and then those readings contributed greatly to the mission statement of saving lives and property from floods in Texas. So again, your measurements matter. These are really important things that are a very, very important part of flood warning systems. Just as kind of a final slide, since we spent some time talking about Hurricane Harvey and flood warning systems and how the data mattered, this was the 7-day precipitation from Hurricane Harvey. And there's a dot right on Beaumont, Texas, right here. For those of you not familiar with the Gulf Coast, Houston's around here, landfall was around here, and the maximum precipitation was right there. And that was 62.07 inches of rain in 7 days. And again, all of these maps, all of these plots, all of this information was validated and made more accurate by those CoCoRaHS observations. And so when you look at something like this and you imagine, 5 feet of water falling in 7 days, we can trust it. And the reason we can trust it is because of all the data that's collected. So thank you, because we couldn't do our jobs without the volunteers we get through the CoCoRaHS program. And NHWC and flood warning systems and CoCoRaHS have always had a very good relationship and a very solid relationship. And again, it's necessary because we rely on volunteers like you guys to do our jobs. So I'll go ahead and end it there, open up for any questions, and just say again, thank you for your time today. And thank you for the volunteer work that you guys do. We really, really appreciate it.
Mark, thank you very much. Very informative presentation, just going through the different gauges and then how CoCoRaHS data is used. We really appreciate that. For you folks out there listening or watching this here, really let you know that, yep, your observations do make a difference, and they are used in very important places. So again, thank you for taking the observations at your location. One thing you may want to do too, if you're a CoCoRaHS observer, take a look at your sighting of your gauge. Just see, Mark mentioned about the trees and that cone out there. In the training stuff for CoCoRaHS, we talk about not putting your gauge too close to a house or a roof and so forth. And so sometimes it's good to reevaluate where you actually have your gauge. Again, we want to have accurate data. So if you get a chance over the next couple of weeks, take a look at that. So, Mark, we'll take questions here in a second. I've got a couple of quick questions for you. So, where are large automated alert systems in the country? Can certain cities are they scattered throughout? Is there more in certain parts? If you give us a list just off the top of your head, that would be really great.
Yeah, sure. So it's a mixture of where there's enough population to get funding for them, which I didn't talk about too much, but funding is always an issue because no one cares about them for the most part until it rains, and then everyone cares about them. So you've got to have the right mix of rainfall amounts that need to be monitored for flood emergencies, plus the tax support and the funding support and the local politician support to keep it running. Texas, Colorado, and California have probably the majority of systems, with the East Coast certainly in the works of catching up. So all along the West Coast in California, LA's got a system, Orange County, San Diego, pretty much all the cities going up there. Denver has one of the largest systems. Houston has one, Austin has one. New systems are popping up kind of in that flash flood alley in Texas that I was mentioning, as population has grown there. Let's see where else. I mentioned the East Coast has some. State of Virginia and Maryland both have statewide systems. Pennsylvania used to have a statewide system that I don't think is currently running anymore, or if it is, isn't as publicized as it used to be. So there's kind of an Overland Park is another big one, kind of in the central U.S. So really, they're kind of all over the place. They tend to follow the mix of potential for flood emergencies and the ability to install a system.
So you would think in hurricane prone areas, this would be a really important thing to have, like along the Gulf Coast where you mentioned. I would think, here in Florida with the storm today, and then also 2 months ago that came through there. Definitely important to have those. But again, you're right. It depends on the money for them and so forth. And then you have to have the maintenance and so forth, the buy-in on that. But in the meantime, again, CoCoRaHS observers, like you said, they can send in significant weather reports. So if there's heavy rain coming down, they can measure, but they're not out there every 2 minutes measuring. And so we do need those automated systems. Tipping buckets, as you mentioned, do have their limitations, but where we can have CoCoRaHS folks around there to back that up with their observations over time, that's really helpful as well. So thank you so much for just educating us on that and letting our observers know that wow, that we'll have to quote you, the gold standard. We were that way. So again, appreciate that. We're going to take some questions out there. Noah, did you have a question at all at all here as we're?
No, thank you. There was one that came up during the presentation and I've lost it now, but yeah, let's go to the answers or the questions coming in from participants here, and I'll step in if I come up with it.
Okay, so let's take a couple of these here, and most of them are comments so far that we've got that have come in. So yeah, just what Sherry asked, should people be checking their gauges frequently? I guess as CoCoRaHS volunteers, not just once a day during big weather events. And yeah, we recommend that you do that. We want you to stay safe though. So if there's lightning out there, or if there's if you're in a hurricane, tropical storm, anything dangerous, the data is not that important as your life. And so we want you to stay safe. That's the important part of that. But if you can check it, if you see really heavy rain coming down and it's safe to go out and report that information goes directly to the National Weather Service on their AWIP stations, and that gives them ample information to help put out possible flash flood warnings and so forth. And any information that we can provide extra eyes and ears out there to help with that is great. And then the nice thing with the CoCoRaHS significant weather reports appearing on those workstations is I was just at an office this last week, and they said that's great because we don't have to go and answer the phone and interrupt our stuff each time. And this comes right across, and so it's helpful. And
Henry, just so I can add though, just to make sure everyone knows that your significant weather report is a real-time report. It's found in the left-hand menu of your data entry page, but we still want you to add everything up and report your normal 24-hour amount at your normal observation time. But these significant weather reports are available in the left-hand menu of your data entry page, and unfortunately not available through the mobile app that many of our volunteers use. So you have to go online to the website to submit a significant weather report.
Yeah, no, thanks. Yeah, thanks for clarifying that. Again, supplemental report, we still want your 24-hour report, but these are real-time things, as he said, and that's important here.
Yeah, and I'll just add, Henry,
sure.
There were some stations during Harvey where the CoCoRaHS gauges did overflow. But again, safety comes first, no matter what. Don't, it's not worth risking your life, not worth checking it if there's bad weather in the area, but there's certainly an advantage to checking on those gauges if it's very significant rainfall throughout the event.
Yeah, and it's funny you mentioned about Harvey, them overflowing. John writes in here, and his question was, he wondered how many overflowed during Harvey. Do you know off the top of your head? I don't remember that as much, but there, again, that happens. We've got a new gauge coming out that we're testing that will hopefully hit the market in 2013. Will hold up to, I think it's 13.5 inches. So for some of those really places where you get a lot of rainfall, these may be very helpful.
Yeah, there's I believe the CoCoRaHS group in the Texas region put together a report about Hurricane Harvey, which mentioned, I don't know if it said how many overflowed, but it definitely talked about it. And so if you're curious to learn more about how CoCoRaHS fared through that, that's a good place to learn more too.
And if you would, Mark, I know we've probably got it here, but if you can send that article from the Gulf River Forecast Center, we'll post that on the webpage. There's a specific webpage for this webinar. If you go to the CoCoRaHS WeatherTalk webinars, again, we'll record this, the slides. I'm sorry, what we'll do is we'll post some of the slides, and then we'll also record today's webinar that you can listen to in the future on that. Okay, let's see. We got more questions coming in here as I look at the screen, and let me make sure I got my right glasses on here to take a look. And let's see. So just more questions about whether a tropical edition of a CoCoRaHS gauge would be there. Yeah, definitely. That would be a definite thing. We would want to put more gauges that hold a lot more. And again, especially in tropical systems that are coming through. Yeah. Does your equipment and forecast do winter weather? So they're wondering about these alert systems. How do they fare in winter weather, or is it for rain, spring, summer flooding events only? And Ray is asking that question.
Yeah, it's a great question. I live in Texas, so most years I don't understand what winter weather is. But it's certainly something that is taken into consideration for flood warning systems. A lot of the ones that are closer to the mountain areas that really get some winter weather, they'll actually shut down for the winter. They might pull the equipment. Those pressure sensors I mentioned can be sensitive to freezing. Alternatively, if that snow information is very valuable, there are some sensors out there that are used that can actually measure snow depth. And then there are tipping buckets that you can purchase that are heated tipping buckets. And so as that snow falls, it will actually melt it, and then it goes through the tipping bucket just like any type of rainfall. When we're talking about heating, that's very, very high power. So those aren't typically ones that are remote stations, but it's something to be aware of. And it's something that in a way can cause an issue. I was actually out maintaining a system 2 weeks ago in New Mexico. And the system starts at about 5,000 feet elevation and ends at about 11,000 feet elevation. And we were doing our winter prep for it. And it rained that day, the day I was driving up. And I checked the rainfall, and every station had reported rain except for one. And then over the next 24 hours, it reported rain very slowly. It had snowed in the tipping bucket, and then it was warm enough to melt. And so that is something we have to take into account. For the most part, the flood threat goes down during the winter. And so a lot of flood warning systems will kind of go into hibernation. But there are some very specific systems, especially further up north, that can have monitoring stations for things like ice dams, which can, kind of suddenly break and cause some flooding impacts too.
Mike writes in and he says, suppose he wishes to use the National Hydrologic Warning Council live data during events on a personal weather website. Is that data available, and is it possible to ingest, or is that all private?
Yeah. So the NHWC itself actually does not host any data. We're kind of more that education group. But depending on your local flood warning systems, a lot of them either have something that's publicly accessible, or it's something that can be, get emails, automated report emails, or even web scraped. There is not a centralized location for all of this information other than the National Weather Service. I don't think they make that easily accessible to download. And partially that's just because it's difficult getting everyone on the same page. But in terms of who actually would be the ones that have all of that data, actually every gauge that is running alert or alert 2, by the way those frequencies work, is required to share their data with the National Weather Service. So they're the ones who actually kind of end up as the stewards of the data.
Thanks. And Matt writes in, and this is maybe a question for us here at CoCoRaHS, about heavy rainfall with gauges and flood-prone places like Florida, Southeast Texas, where they overflow, limited to the 11.3 inches and potentially lost due to site damage, inaccessibility of data, unavailability of observers. Do we have any feel for how many sites don't report such situations? And I'm not sure on that one. We really don't know. Sometimes we do, a lot of people don't report during those tropical systems. We do have folks actually reporting, but yeah, things get swept away. I know the Bahamas, we had some devastating hurricanes there in the last couple of years, and they kind of wiped things off the map. So not everybody is reporting during those. And so again, safety is the most important part of that. Well, I think that kind of sums it up for today, and we really appreciate you taking the time. We'll have this information and any other resources you want to send us, we'll post on the website. Again, thank you very much and for your support over the years, and we continue to enjoy our collaborations with you guys, and anything we can do to help, we appreciate that. So thanks.
And thank you. Appreciate the time today and appreciate the chance to talk to everyone.
Well, folks, as we close out today's program, I want to let you know our next Weather Talk webinar will be taking place on Thursday, January 19th, a little more than 2 months from now. It's one of our annual favorites, where meteorologist Greg Carbon of NOAA's Weather Prediction Center will review the top weather events of 2022. So you won't want to miss this one. We currently have, we will shortly have, there we go, a registration form up on our website where you can sign up for that one. And before I forget, when signing off today, please take the survey that'll pop up on your screen. Well, so until we meet again, stay safe and healthy. This is Henry Regis for the rest of the CoCoRaHS team saying goodbye for now and wishing each of you a wonderful holiday season ahead.